Most of the integral applications we've looked at so far have been what we call geometric, so we're looking at how to find areas and volumes. This is an example of an analytic application of integrals. So what can we do to continue analyzing functions? So differential equations, there are whole courses in college devoted to solving different kinds of and understanding different kinds of differential equations. So this is just a brief introduction so you have some idea what people are talking about when they say differential equations. So a differential equation equations involve functions and their derivatives. So there's some things, chances are we've probably worked with a few differential equations already. So generally what we are doing with differential equation is we're trying to solve them for the function. So to try to get back to the function if we know what the derivative is. Okay. The order of a differential equation is the highest derivative that is involved in it. Okay, so like for example, if we have 3y to the fifth plus y prime minus 2y with the fourth derivative, may not have seen that notation in a while, it's been a long course, fourth derivative plus y to the power of 7 equals 8. So this is a differential equation of degree 7, because that's the highest power of y, still uses the same terminology, and order 4. So this is a fourth order differential equation because we have a fourth derivative in it. So a really simple differential equation that we have certainly seen before is dy dx equals some function. The derivative equals some function. So y equals the indefinite integral of f of x dx. Okay? So we have a technique to be able to solve differential equations that are a little bit more complicated, that involve both y's and x's. And these are a lot of the kinds of differential equations you're going to see where the derivative is dependent on both y and x. Think of a derivative of some kind of curve that's not necessarily a function. Okay, so we have dy dx equals negative xy. Okay, so what the technique that we're going to use is called separation of variables. Okay, so we want to get the left-hand side just in terms of y, so we can multiply both sides by dx and divide by y. So the left-hand side is dy over y, so left hand in terms of y, so y's and dy's on the left, and right side in terms of x's. Right hand in terms of x. And then we are going to integrate both sides. We get the integral of dy over y equals negative the integral of x dx. Okay, so we have, on the left side, we have 1 over y, which gives us ln, the absolute value of y, equals negative x squared over 2 plus c. Well, if I want to get rid of an absolute value, if I want to get rid of an ln, I can raise e to the power. So one thing to remember is e to the ln x equals x, because what the natural log of x is saying is what power do you have to raise e to get x. And if you raise e to the power you have to raise e to get x, you get x, sort of in the definition here. So e, we're going to raise both sides to the power of e. We're going to take e and raise it to the power of both sides, and that's applying the power rule, which we did way, way, way back when, which says you can raise two things to the same power. I think that's pre-calculus 12. You can raise, if you raise two things to powers that are equal, the result is equal. So e to the ln y equals e to the minus x squared over 2 plus c, and that is one exponent. And so the absolute value of y is e to the negative x squared over 2 times e to the c. We're just using our, this is our constant. Okay, so this right here is going to be our constant. Y e to the power of c, we're just using our exponent rule, that if you're adding exponents is the same as multiplying. So we're going to let e to the c equal a, just as a different constant. So absolute value of y equals a e to the minus x squared over 2, and y is equal to plus or minus a e to the minus x squared over 2. Okay. And notice that y equals 0 will also work. Okay. So the method of separation of variables is going to work for dy dx equals f of x times g of y. So if we have a product of two functions, then we can integrate it like this, where you have dy over g of y equals f of x dx.